Welcome back to the New Quantum Era. I'm your host, Sebastian Hassinger. I've got a very special guest for this episode. I've interviewed him before. In fact, just a few weeks ago, I repeated our episode from last spring, where I talked to him at the APS Summit. But whereas in that conversation, we were focusing on the work that he's currently undertaking, I wanted to revisit the conversation in light of recent developments. The Nobel Prize for Physics in 2025 was awarded for the discovery of macroscopic quantum mechanical tunneling and energy quantization in an electric circuit. This is work that was undertaken by John Clarke, Michel Devoret, and my guest today, John Martinis, at UC Berkeley in the 80s. By introducing microwave control and readout of these devices, they laid the foundation for the use of superconducting circuits with Josephson junctions as the basis for superconducting qubits, which have been crucial in the development of quantum computing to date. And connected directly to John Martinis' more recent work with Google and currently with his startup CoLab. We did encounter a number of technical difficulties with this interview. We had some network issues that we had to work through. So I have edited together this episode from all of these bits and pieces. I hope I've done justice to the conversation and to the subject matter. I really thank John for his patience in working through those technical issues with me, and I hope you enjoy our conversation. All right. Thank you so much for joining me, John. Congratulations on the honors of the Nobel Prize this year in physics. We've talked before about your work in superconducting devices and quantum computing. I'm really interested, you've talked about how the Nobel has given you an opportunity to sort of have a lot of conversations and sort of think back over, examine the sort of the history of these devices. What's been sort of the sort of new insight into the science and the technology of superconducting devices that sort of come to you through this process?
Well, of course, the basic idea here is that although we normally think of quantum mechanics as the physics of the small, fundamental particles, atoms, molecules, and the like, it's actually a much more general phenomenon. So, for example, you build a synthetic device, we call it, with a macroscopic variable, such as an electrical circuit. And if you set up the conditions right, you can see quantum mechanics in that too.
Right.
And what's basically happened is from that experiment and many other experiments, people doing tremendously clever things, people have been able to build and design and test many kind of these macroscopic atoms or synthetic atoms, if you like,
right,
over the years. And it's turned into a very nice field in itself. And clearly it's interesting because of quantum computing. And I like to think of it as you normally think that your fundamental building blocks are for quantum as a periodic table and electrons or whatever. And now it's also capacitors, inductors, Josephson junctions. Actually massive small micromachine particles. So that's the mass that is quantum mechanical, center of mass, maybe
right,
nanomagnets, things like that. So there's a whole new class of quantum physics that we can study.
Yeah. I mean, that's very interesting. As you said, it's sort of that recasts them as almost the Lego bricks of that we have to build new devices. You've mentioned it's been a very long road for superconducting, right? I mean, superconducting devices. Josephson hit upon the tunneling effect in the early 60s. I remember him saying he actually was told in a workshop in a public setting by Bardeen that he must be totally wrong.
Yes, exactly. Yes, this was
Which is
very surprising.
yes,
And there's a
and then
technical reason for that. I've written a paper that goes through the technical calculation. I don't know how new it is, but it's something I wanted to understand
yeah,
deeply, and also to understand it to know how we rely on this effect to make our qubits. And I wanted to understand kind of more at the microscopic level what's going on. But yeah, it's kind of subtle what's going on. It's a second order quantum effect, and I can see why someone as brilliant as Bardeen
right,
could
right.
could not get it at the
Couldn't wrap his
time.
head around it. So the tunneling effect was validated experimentally at Bell Labs a few years later, and then Ford Labs, which used to have an industrial R&D division, built the first squid, the superconducting quantum
Right,
magnetic field
interference
detector.
device.
Right. Thank you.
Right.
And so that was kind of the first inkling that, or an attempt to make something useful out of this new device, this Josephson
Yeah.
junction.
Well, people always understood that superconductivity was useful, but then that kind of opened up device physics based on the Josephson junction.
Right.
And the first thing was to build, these squids. But if you look at John Clarke's thesis project and his work in Cambridge, he was trying to measure very small voltage. And I think in the Nobel lectures, he's going to go into that,
Great.
which is really good.
Great.
Okay, so talk about the early days.
Yeah.
And then the people were trying to make classical computers with that in the late 70s,
Really?
early 80s. Yeah.
Interesting.
And people are still trying to do that today. They have single flux quantum logic,
Right.
but there was a big effort at IBM at the time
Huh.
when I was a graduate student. So that's late 70s, 80s. And, people trying to do that.
I guess I'm probing at what you were saying about the macroscopic quantum tunneling of Josephson junctions providing a portal to see into the subatomic level, see the behavior of the subatomic level at a macroscopic scale. That really is at the root of the interest of these devices right from the very beginning, right? And I mean, would you say? I mean, Tony Leggett, another Nobel Prize winner, sort of famously tried to create a call for people to demonstrate macroscopic quantum behavior. And that was primarily around these superconducting devices, right?
Yeah, well, that was the call. And then he understood superconducting devices and he knew that would be a way to test it. And, at the time when I first learned about that, this was actually at a low temperature 16, I think in Los Angeles. There were, some papers on it. There's a lot of discussion. There was a little bit of data, but it was not very conclusive. People really hadn't understood exactly how to measure it yet and do it properly. But, as a student, it was clear that all these people were thinking about it and it was a great topic and should be investigated carefully. So, even as a student, I recognized this was interesting. Yeah. And actually, looking back, I don't understand why more people didn't jump on this. But, the technology was a dilution refrigerator and everyone was used to just doing it in helium. It was some more advanced technology you had to feel comfortable with.
So one of the things that I think is really, so we're getting to the point where you take a class with John Clarke, I think as an undergraduate, right? Initially? Or was that during your master's?
No. I was working in another group as an undergraduate, but then I moved to John Clarke's group as a graduate student.
Okay, but you took.
But I took a class from him as an undergraduate.
Yeah, exactly.
And what maybe hasn't been I talked about previously is that at that time he was doing research where people were looking at quantum noise effects in these superconducting devices.
it's getting to exactly the thing that one of the main things I wanted to talk about. So you had been a self-described electronics tinkerer.
Right.
These Josephson junctions, as you just described, were being seen as DC devices. Where
Yeah,
did
low frequency
low
device.
frequency?
That's
Yeah.
right.
So when at what point did the thinking shift to microwave signaling control and readout and a resonance interaction?
Yeah, well, we did an experiment, and we kind of wired up this as we would wire up a normal Josephson junction experiment, and it completely failed. And
Right.
we looked at the thermal escape rate from 1 to 4 Kelvin. It just didn't make any sense at all. And we had an idea how to analyze it at the time. And as soon as it didn't work, it's like, okay, let's rethink this. And then we sat down and thought about it very carefully. And I think it was pretty soon that we understood we had to filter it, especially at microwave frequencies, and that we wanted to make sure that the junction looked into a very well-defined microwave impedance, microwave circuit, if you like.
Right.
And, we did microwave experiments and the like to check that all out. So it's just we did an experiment, didn't work, and then we just figured out what it had to do. And once we did all the careful things, especially the filtering, but it was really basically everything we had to change. Then the data made perfect sense. Okay. And at that point, we had to improve things and think about it, but it was a matter of getting a dilution refrigerator working, getting to the low temperature, and then making everything compatible. But it just kind of came out, logically from that point.
Right.
But again, I think that, people knew that it was oscillating at the Josephson frequency, whatever. But it was not the fundamental concept we had to understand.
Right. Right. Well, and I mean, at least in my mind, that's such a pivotal moment because the development of Josephson junctions into qubits is really a story about developing the microwave control and readout. I mean, that is still to this day, that's the challenge.
And still people are working on that. And that happened for a long time to figure out the various tricks and, what materials to use, how to isolate the junction in the proper way. We were just doing very rudimentary experiments at that point, but it got us in the right direction. So that was what was key.
And most importantly, you experimentally proved that this macroscopic quantum effect was happening.
Right, exactly.
Which
of course showed that it was interesting effect.
Exactly.
The other thing that happened there, and I would say in the next few years, is as we did more and more sophisticated experiments, we could do a clean experiment, know what's going on, get it to work exactly as you would expect from theory. So, we gained confidence that was a clean enough system to do more and more sophisticated experiments. Right. Each experiment led to the next experiment. The way I like to think about this is sometimes you do an experiment and you kind of fall over the finish line. And then it's going to be hard to do the next thing. And I would say that's not what happened. Every experiment we learned a little bit more for the technology and the physics, and then we could build on it. And other people did too, of course.
Right.
So that's what made it so interesting.
Right. Yeah. And in fact, I think Yasunari Nakamura in 97, 96 demonstrated sort of the two-level system, right? Which is really, that's the next sort of giant step towards this being a component in a quantum computer. You talked about that sort of thinking about these devices being potentially interesting for quantum computing, sort of being in the air before then too, right?
Well, when I was writing up my thesis, there was a nice conference at UC Santa Barbara where Feynman talked about building a quantum computer. So it was kind of conceptually out there.
Right.
But some other theory work was developed, other things developed to the point where it's like, okay, now we have to make qubits and make sure we know how that work and the like. But that was the next big step is showing that. But I'm going to say in the 10 years that happened, we and Clay Group and other groups were doing a lot of experiments, kind of looking at the energy levels and looking at the quantum physics. And I'm going to say it took about 10 years to understand quantum devices and learn how to measure and understand, so that by the time that more of the qubit experiments came along, the technology had developed far enough to start doing those experiments properly.
Right.
But I would say the big moment, that was important experiment very clearly. And then there was U.S. government funding to look at these. And then, people really started looking carefully about it. That's what happens. Okay.
Yeah. So a certain algorithm caught the attention of the U.S. government and the national intelligence community. But that also brings another point in here, which you and I have talked about briefly before, which is the atomic clockwork, the molecular beam, and then the laser cooling, all that work. Dave Wineland and others, Chris Monroe at NIST.
Oh, by the way, they were down the hall from me.
Yeah.
Right. So,
right. But I mean, in a sense, they had a lower bar for proving that this was quantum phenomena that they were dealing with, because they were interacting directly with an atom at a subatomic scale, and so no one was questioning it, right? I mean, in a sense.
So but what was interesting at the time is we started doing experiments on single atom systems.
Right.
And up until then, people had always been doing, ensemble measurements.
Right.
Okay. And you kind of take the average of the signal, but doing single measurements. Now, we were doing single measurements at the time, but I would say the ion traps and what David Island, especially with the quantum jumps, was really much more spectacular and directly showed you that there were some strange things going on that you can now understand. Right. And that was definitely a big thing. But they were looking at natural atomic systems and then cleanly looking at the atomic physics in those systems. We had a while to catch up to that.
Of course, but this is my point. You were building up this foundational set of techniques and knowledge and understanding, and turning it into a technology, a synthetic atom as a technology that was, as you said, you were doing. You were interrogating a single quantum system, but in this synthetic setting. So it makes sense that there was a lot more work to be done to get to sort of the acceptance that was what you were actually looking at.
But all that said, that was happening also in the atom physics community too. They were learning how to trap and manipulate single atoms or few atoms. The neutral atoms were learning how to condense them.
Right.
So there was a real renaissance of building these systems. Mm-hmm. And, we were just building them in totally different ways, of course. Yeah. But just kind of the ideas were just in the air, and everyone was really working, and everyone was understanding this was exciting and new and important. Okay. Yeah. And, of course, that attracts the best people to that field.
Yeah. And it's, important and new and exciting, and in two sort of mirror images of each other, right? I mean, there's exploration into the fundamental physics of the universe, that these, being able to probe single subatomic behaviors and phenomena is driving our overall knowledge, our scientific knowledge, but it's also. It's so interesting to me to see this march towards, as you said at the beginning, these building up of these Lego blocks, these building blocks of techniques that can be turned into the transistors and the capacitors of this quantum sort of technological context, and that seems to be almost I mean, I wouldn't force you to pick one or the other, but it feels to me like you're motivated by the technological advances, almost.
I enjoy doing
Yeah,
all the fundamental physics demonstrations, but yeah, I was always motivated. Once there was funding for doing that, it was motivated for the science in the beginning, and then when you saw the quantum computing application, it's like, well, I want to build a quantum computer, but
right,
to get there, we have to have fundamental understandings. We have to do the technical advance, and
right.
I'm a little bit more on the technical advance side.
Yeah,
And
but the two
that's
are hand in
what I
glove,
like.
right? Yeah, that's so. I mean, I find that so fascinating, and in fact, these devices that we're building, the other than Shor's, the other, sort of, in fact, Feynman's point in 1981 is if you want to simulate nature, you're going to need a quantum computer to do that efficiently. So we're
Right.
actually building these machines, which their clear value in driving our fundamental understanding of the universe is well understood, right? If you can
Right.
build a large scale many body quantum system and control it and observe it, we probably are going to learn a lot. I'm imagining.
Well, and that's what I was able to do in my career. We did with these simple experiments. We learned about quantum devices. We started working on qubits and learning how to do that, how to couple them together. A big event for me was writing a paper on how the surface code worked, more
Right.
translating it so that us mere mortals could understand it. Okay. And then with that, it's like, okay, I want to build a chip to do this. We were doing that at UC Santa Barbara, then moved
Right.
on to Google. And now, that has progressed to a very good, level. And it's like, well, okay, now we have to learn how to manufacture it really
Yes.
reliably, really well. Get rid of some of the problems that we see. It's just another evolution of the technology.
Absolutely, absolutely. And do you? So in my mind, there's again going back to the evolution of these devices from simple demonstration of quantum tunneling to a two-level system to gates and more and more fine-grained readout and applying error correction. It feels like there's also cross-pollination of the techniques that are being developed in all the various modalities. So there's now bosonic modes within superconducting qubits that are being used for error correction, GKP designs, for example, or
Yeah,
you know
there's many ideas out there
right.
now, and many things people are working on and perfecting, which is makes it feel very interesting. Yes.
Yes. But I guess I wonder if do you see the increased sort of sophistication of the individual device of the qubit and the QPU, the quantum processing unit, as evolving into it's incorporating all the best learnings of all these techniques that come out of these experimental validations of theory or vice versa, that
Yeah, I
sort of
could say that obvious is happening, and
mm,
people are doing that. I my and that's what most physicists are doing, and that's really great. Okay. However, my idea right now is that we pretty much know how to make decent qubits, and there for me there's advantages to the transmons. People are building other
mm,
things, and that's great, but I see a real advantage to doing it right now. And what we have to do is just fabricate it better, and
right,
fabricate in a way to improve the wiring and other stuff like
right,
that.
right.
So it's more for me. A lot of other people are working on the physics, and that's great. I
Right,
love
right,
it.
right, right,
But for me, we're trying to solve the hard part, which is the fabrication part.
right,
And in specifically, you can use kind of academic level fabrication to make these devices, and that's been
right,
very powerful. And we just want to move beyond that
right,
because we think
right,
we have to be much more sophisticated to get the yield up and do it right.
right. In a
So
sense,
and that's hard for most people to do
yeah.
that. And also it's scary because you're doing something totally new, and everyone says, well, our qubits aren't better than other qubits, so what are you
Right.
doing? It's like, well, yeah, it takes a long time to like fabricate things properly,
Yeah.
and
And in a
but
sense that
that's the risk I'm willing to take. It's okay.
And I in a sense, that's putting the weight on the technological advancement side of the balance as opposed to the scientific advancement, right? I
Yeah,
mean, these
okay.
are
Yeah,
these are well understood systems, the
but
transmon.
look at CMOS.
Right.
Okay,
Exactly. Exactly.
why are our computers so good? I mean, this
Right.
was kind of fundamental ideas invented,
That's
many
right.
many decades ago. But it's only the technological advances, which are very hard and
Yes.
involves, very complex science.
Yeah.
Okay, so I enjoy this kind of science,
Yeah.
and in
Yeah.
fact,
Yeah.
I have a funny way to look at it. Is that a lot of times, people are inventing new qubits, like, and that's hard, and that's it. But you're basically putting the design and integrating the Schrodinger equation, which we know works. Okay, and it's hard and it's great. Okay, however, when you try to fix materials, that's just really hard, and you have to do trial and error. You have to,
Yeah.
use your intuition and the experience of our collaborators and whatever. And it's a much more, let's say, of a discovery mode
Right.
to do it that way, because you have
Right.
to figure out, what the real problems are, and it's hard to do the experiment. So
Right.
I like that challenge, but mostly that's not, other people aren't doing that. So
Right.
if we're successful, I think we're going to be successful. We're going to do something really unique.
Yeah, I mean, in a sense, it's seeing how far you can go from MQT demonstration, two-level system demonstration, gates, et cetera, to like the transmon, and like how far, is the transmon going to end up being that fundamental building block that unlocks the type of scaling that you get with CMOS
Yeah,
and the
and there's
transistor?
reasons why I think that's so. But on the other hand, if I can fabricate really well, then let's say we can get the
Right,
reproducibility of the junctions really good, then all these other qubit
right,
modalities now
right,
become possible because we
right,
can make the qubits better.
right.
So, in some sense, I'm trying to help everyone,
Yeah.
by solving the problem.
I think anyone working on any hard problem in a technology at this early stage is working for everybody, because the
Yeah,
problems
that's
are
right.
so hard. The motivation has to be sort of very broad in scale, I think, and
Yeah,
the
and
impact.
I understand most people wouldn't want to try this because it's just a lot harder. Okay, it's very simple,
It's
but
really
we
hard.
already know from some experiments that if we can do it this way, there's potential to improve some of the problems everyone sees,
Right.
and that's something that I think would be really great. But but it's
Yeah.
actually very hard for our company because everyone compares us to all the
Yeah.
other
Of
superconducting
course.
companies. It's like, well, you're way far behind, and it's like, yeah, we're trying to do something totally new. Yeah, we
Right.
expect to be behind. We're making progress, and of course we don't talk about it much. But then if we get this to work, we're going to just jump ahead in terms of how reliably we can make things and scale things. So
I
so it's
like the
only
idea too.
people don't understand that, or obviously we don't have the data yet, but that's
Right.
okay.
Yeah. No, and I like the idea of your success in this company's sort of goals will potentially provide fabrication techniques that will have extremely broad impact, right? As you said, if you can fabricate Josephson junctions at a another couple of orders of magnitude in terms of quality, overall quality, then
Yeah,
that's
but I'm just going to give you an example
yeah.
of how like insane this is for me. Okay, that people wonder what we're doing, whatever. If you look at a roadmap of a leading company with superconducting qubits, their roadmap is 120 chips, 120 qubit chips, and then you use those dies and piece them together to make bigger and bigger things. So if you want to make, a million qubit quantum computer, and you have to piece, 10,000, 10,000 of those. That's kind of hard, okay? And so the fact that we're trying to wafer scale up to 20,000 qubits and do it in a way where we can yield. The problem they're doing 120. My guess is that it's hard to yield.
Yeah.
It's hard to get everything to work. And, that wouldn't surprise me. And that's actually what I've seen from other people with the technology. And it's kind of funny. No one wants to talk about it because it's a negative of what they're doing.
Yeah.
You can kind of tease it out from the roadmaps if they talk about it. And it's like, well, we're trying to fix that.
Yeah. In that sense, what you're trying to work on is the quantum equivalent of the monolithic solution, right? The need for the monolithic solution was driven by all of those hand soldered joints, and you get to 1,000 components in an electronic device, and it would definitely fail because there'd be one joint that was cracked.
Yeah. So there's a nice way to visualize that. If you look at the superconducting qubit devices now, in the dilution refrigerator, and you look at it, there's just a mess of wires, a mess of microwave components, whatever. Okay, really complicated. We know how to scale to put it onto a chip, this size. And that's a true integrated circuit. Yeah. Right now, it's a bunch of wires that's probably 95, 99% of the volume, and then a chip in the center. And in fact, if you go back to the 1960s and you think about TTL and whatever, you had the little transistor gates, and they had all this wiring going around to connect it up. But there it was actually better because you could separate out the transistor gates with the wires. For quantum computers, it's all on one chip, so you have this escape wiring. So ours is even worse. And we're just trying to fix that problem. So, we wrote a paper, we have a proposal, we wrote a paper, we're trying to do all that. And it's just strange because some people understand that, but other people, it's like, well, if you can build us something to solve all our problems in 6 months or a year, then, we're interested in it. And it's like, come on, this is not a trivial thing.
How many qubits are on that chip you just held up, John?
Yeah. Okay, we're going to start with the few
the one you just held up. Is that one of your chips?
Well, this would be 100 qubits. Okay. But then the 300 millimeter wafer would be 20,000 qubits. Okay, right. You could do that, but you have to start small to find out what all the problems are. But what we're finding is, we're trying to do something radically different. It's not a trivial thing at all to do this. And, people have tried it and other things, and it's a small part of it, and they don't work very well. So we thought about doing it that way. We don't think it's going to work. We're trying it our way. We actually have a second new way to do it, which is really, really interesting. Maybe we'll talk about it in a couple months.
Cool.
We're really excited about, the possibilities there. It just takes longer.
Yeah. Yeah. Well, as you said,
but we're being graded against a 20, 30-year-old technology.
Sure. And also the expectations of private capital in particular around emerging technologies over the last 30, 40 years are, is that 3 to 5 year, the stereotypical 3 to 5 year timeframe for getting to some kind of, technology that can build traction in the market. And I keep telling people, we've reset the clock to the late 40s or early 50s with quantum computing. And if you were a venture capital in 1950, what would your portfolio investments look like for investing in classical computing? I wouldn't have a 3 to 5 year horizon.
I think even the most rudimentary computers had uses in cryptography and ballistic tables or something.
Yeah.
So there were some early use cases because
that's true.
The competition was by hand or maybe some simple punch card thing.
That's right.
But that's what you. The frustration for me is that if you're kind of very optimistic and maybe naive about all the real challenges, what are the challenges, then you can sell a simple, exciting, optimistic story that people will go with. When you talk about, well, things are harder and you have to do all these things and develop this complex technology, well, then you can't make money so fast, and that's harder to want to fund. Well, but our view is there's a tremendous potential. We're solving the problem so that we can build this thing. but it's very hard for people to do. But I don't want to sound too negative, but what I would say is my experience for doing this for 40 years or so is when people don't understand and this kind of thing is happening, you have a really good idea.
That's right.
Okay.
That's typically true.
Because it's hard to understand, and I think I can look into the future, a little bit better than some people can, and there's a realist in terms of getting things done.
I suspect that the Nobel Prize Committee's decision will add to to validate the fact that you are on the right track, that you know what you're talking about.
Well, yes, we've obviously seen that. I like to put it that we now have a celebrity endorsement for our company. And celebrity endorsement, in fact, works really well. But the other thing is, even though that happens and people congratulate me and whatever, they still revert back to their old thinking. Okay. And again, it's just, in my view, validates that we're doing something really transformative. And, of course we have to get it done and the like, but, it's normal when you try to do something out of the box. Most people want to do something incremental.
That's
okay.
Right. That's right. Well, I mean, thank you. It's great to me to see how the Nobel Prize sort of validates again, sort of your thinking, your work all the way back from the mid '80s. But you're also still, it validates the fact that you're still doubling down on seeing how far you can take this technology, and it has a real chance of being that transformative, disruptive, foundational layer that really brings quantum computing to scale that it needs to have global impact. So thank you very much for your time. This has been really, really great. I heard you say you'll have something else to talk about in a couple months, so you'll probably be back on the show at some point soon. So this has been terrific.
Well, this is a very interesting technology that exists right now, and it's been fun working with this company to use this application, and it'll be. I can talk a lot about that. If you want to talk a few more minutes because of the problems we had, I'm open. Your questions are very interesting, so I'm willing to.
Thank you. I mean, it's the reason that I really enjoy talking with you is I think that you do encompass these two sides, right? I mean, there's the experimental physicist view of things, and then there's the systems engineer and computer engineering kind of view of things. And that's why, I mean, combining those two is no small feat, because they really are two different lenses for deciding what your next experiment is going to be, deciding what the challenges that you're going to try to tackle, deciding on your methodology, deciding on what the end goal is, right? There's curiosity-driven scientific experimentation where it's like, let's see what happens when we do X. And then there's engineering-driven experimentation, which is how do we solve problem Y, right? It's much more practical. And I guess what I'm wondering is, has that sort of been something you've been consciously trying to resolve the tension between? Do you feel that tension between the two, or has it been sort of just following your natural instincts?
So this is a little bit of a natural instinct because I've always thought about instrumentation. And it's actually interesting because I think I've always been this way, but I learned that from John Clarke, and John Clarke came from Cambridge. And if you look at my scientific family tree through John Clarke,
right,
there's all these people who built instruments that mass spectrometers, cathode ray tubes, all these things that led to scientific discoveries. Mm-hmm. So instrumentation is kind of in my family blood, if you like, through John Clarke. So I've always thought that way. But this was more physics instrumentation. And what happens is when you want to build a computer, then it's a different kind of instrumentation. That's really systems engineering.
Yes.
And what happened is, I think I was always thinking this way and thinking globally about all the things we had to do. But after I left Google for a variety of reasons, I started thinking about, what were some of the areas of conflict. And the big area, I think, was I was a system engineer.
Hmm.
And, people have ideas to do this or that. And it's like, oh, I'm always filtering it through a system engineering. And then I have let's say negative things to say because it doesn't make sense from a system engineering point of view. And what happens is at that point, I read a book and thought about it and really realized that there was a whole discipline involved in this. And I learned some of the principles of that, which completely explained how I thought. But the
Right.
most important thing is I realized that the system engineering is kind of completely opposite from what you do as a physicist.
Right.
Okay. And then it was like, okay, yeah, I can understand where there's a lot of conflict, coming about from this.
So
And for
what in
example, our
yeah,
company,
what
to,
yeah.
to do the fabrication, this is totally a system engineering thing. We have to fabricate really well. Whereas I think people are now is like, okay, we make it a certain way, it works really great, and fine. And my statement is, yeah, that's great, but you're in a box canyon, and at some point
Yeah.
you aren't going to be able to get out of that, and that's a system engineering issue. And
Right.
and of course, people don't want to see that, and they're
Right.
optimistic they'll solve it, even though it's been unsolved for a decade or more. So
Yeah.
it's a, and I would say, I think that gives me, let's say, a superpower, if you like. Okay, but it also means it's my kryptonite too, because I think so
As
differently
always.
than anyone else. But it's
Yeah.
fine to think differently, okay? Especially if you're starting your own company. Okay,
Yeah.
this
Yeah.
is fine.
Yeah. You mentioned your physics family tree. At one point when we were talking in the past, so after Michel Devoret joined you at Cal, he was postdoc when you were a PhD student under John Clarke. And then you finished your PhD and you did your postdoc at Saclay.
That's right. I went and joined them. Yeah.
And you had talked about how the French approach to physics affected your sort of your overall thinking. In what way would you describe?
Well, in the United States, there's a general understanding that, you build something, take data, and then figure out what nature is telling you. Okay. And that's certainly, uh, John wasn't quite so far that way, but that's just the way, people think. And of course, when Michel came, we had a lot of discussions about what the theory was and understanding it better. And that was really the French way, is to really do
Mm,
a careful theoretical analysis and understand the experiment really well, and then go ahead and start building something. And
mm,
what I always says is sometimes experiment you should do it the American way, and sometimes you should do it the French way. But
right.
what I think is more important is when you start the project, you say, is this going to be a French experiment, or is this going to be an American experiment? Or maybe some combination of the two. And it's always some
Right.
combination of the
Yes,
two.
of course.
Okay.
Of course.
And I think, that realization, when I went there, it was really good to understand. And again, there's pros and cons of every approach, and you just have to. But it's nice to have that toolkit of doing it
Hmm.
both ways.
Absolutely. Absolutely. And so the now Michel Devoret has now joined Google at UCSB. Is this sort of are you interacting with him now in the UCSB setting at all?
So, with the Nobel Prize, we've been
Yeah.
interacting a lot. So, yesterday I did an event at Google in Palm Springs, in fact, and tomorrow we're going to do a Q&A with students. And we very much enjoy this kind of panel Q&A
Sure.
because we look at things in such a different way. I think it's interesting, and we learn from each other. So, we're doing that. I'm so busy with my company and he's
Yeah.
busy with Google. We try to get together. What I find really sad is there's a tremendous number of things we can talk about. But because we're in businesses, we can talk
Yeah.
about 5% of that. And I find that really sad, because I'm sure if we could talk freely, we could solve like 10 problems in the next 2 months
Yeah.
to,
Yeah.
to make the field better. But okay, we just can't do.
Yeah.
Unfortunately, we can't do that. I'm trying to figure out a way to do that, but I think that's
Yeah,
beyond
it
my.
feels like there is still, I mean, big parts of this are still in a pre-competitive stage, an
Yeah.
open science stage, and certainly the role of the public sector, the National Quantum
Oh, but
Initiative
yeah,
in the
I'm talking
U.S.
more about the Google part. Of course,
Sure,
with the UCSB stuff, we can talk about it,
right,
and that's fine. But in terms of the Google stuff, which is more, what I'm trying to do, it's the details of how to
right,
scale up a qubit. That's fine. But yeah, Michel has both, his UCSB research and Google research. And when I moved to Google, I just put all that more into a practical direction.
right,
And that's the way,
right.
that's why we're retired at UCSB,
I see.
to really
Yeah, yeah,
focus on the practical aspect. And again, if we're collaborating with big semiconductor companies, then that's less what you can do with a graduate student research.
yeah, yeah. I think we've hit all of the topics I wanted to cover. Is there anything that we haven't talked about that you wanted to talk about?
No. This has been quite nice, and
Good.
yeah, thanks for going through various things.
Sure.
But I would say that the interesting thing is, once we got this started and other people got involved in it, there are just so many creative ideas from around the world
Yeah.
that push forward the project. And I would think what was really great is that the different research groups weren't trying to outcompete with each other and do something a month ahead of another group and scoop them. We were all kind of doing our own things and exploring it and then talking about it publicly so that the field got better. Now, around 2010 or so, then it started being much more corporate and we stopped doing it. But we were far enough along that, it was okay at that
Yeah.
point. And obviously, there have been a lot of open academic
Sure.
things that have happened since then, too.
Yeah.
So, the evolution of the field, I think, was good and people were, cooperating with each other, competing but cooperating in the
Right.
proper way. And that's
Yeah.
why I think that's why the field has progressed so well.
Yeah, I would agree. And I mean the experimental physicists and the theorists who can start testing theory on actual quantum hardware are kind of like your first customer for a quantum hardware device, right? So
And
there's a
lots
nice
of nice
collaborative link there.
happening.
Yeah. Excellent. Okay. Well, let's wrap up. I'm going to see what I can edit together out of the bits and pieces. I'm pretty sure I've got a pretty good episode here.
That's it for this episode of the New Quantum Era. I think I did end up editing together a pretty good episode. Apologies for any pieces that were difficult to follow. Thanks again to John Martinis for his infinite patience and his technical advice.
I think what we should do is rejoin and try to see if the connection gets better then. Now, we have to make sure that you get the recording so far.
This has been a production of the New Quantum Era. You can find past episodes on newquantumera.com on the web and connect with us on Blue Sky at newquantumera.com. And if you enjoyed this episode and the podcast, please tell your quantum curious friends to give it a listen.